Hey guys, um, yeah, sorry I've been away for a while. I've actually had some, I don't even know how to call them. I've had some personal troubles, and I finally realized that I needed to do something about my mental health. But I'm happy to say that I have gone and done something about my mental health, and I'm doing very, very well right now. And I finally found the motivation to come back to YouTube videos. And hopefully, this will be the first video and like continuing the one video a week thing that I was into a few months ago. So, without further ado, this video is brought to you by Poor Decisions again. So, as you can see in front of me, I have this thing. Ignore the we're going to talk about that in a future video, and maybe even that if there's interest. This is a before before man landed on the moon signal generator made by the glorious Hewlett Packard back in 1957 or thereabouts. That corresponds to a few of the date codes I saw inside the unit. It's basically an RF signal generator from 10 megahertz to 420 megahertz. And being over 65 years old, it's older than both my parents. It's older than any other piece of test equipment I own. And it's been heavily used. It comes from academia, basically. I don't know where the university got it before that. I only got it on condition that I don't sell it, which I don't intend to, because just look at it, it's glorious. And I thought we could take a look at it and discuss about it and see what's up, basically, and how they used to make test equipment back in the day. This is from basically the early days of Hewlett Packard, when they were in my opinion, the most important company in the entire universe, world, whatever, what you want to call it. HP, back in the day, HP were the test equipment manufacturer, basically. So they were the creme de la creme when it came to everything, from signal generators to multimeters to oscilloscopes, everything. And they sold their test equipment division, I think, to Agilent a while back, and now Agilent sold that test equipment division to Keysight. And what used to be HP is now Keysight. What the other sides of HP were into, like computers and calculators and stuff like that, still exist under the same brand, but having lost basically all of the spirit that was associated, at least in my mind, with what Hewlett Packard actually stood for, which was test equipment and doing it better than anybody else. Some might argue that Tektronix also fit in there as well. Tektronix being more into oscilloscopes than HP, but yeah, I don't know what to say. I love Tektronix, don't get me wrong. As you can see, I have quite a few Keithleys, and like the more recent ones are actually, they say they're a Tektronix company. So, but I've never owned a Tektronix oscilloscope, and I don't think I ever will. Right. You can see, by the way, that the Doom playing scope is gone. I had no need for it, and it went to a better home. And there's a few changes in the layout. Maybe we'll discuss them a bit later. But first of all, let's turn this thing on. There's one dead thing, which is the power level meter for the output. And the rest of the thing works perfectly. I'm going to show you on the spectrum analyzer a bit later. I apologize if you hear it humming away in the back, but it's it's warming up. So what we have here is a 608D, sorry, signal generator. It has a few ranges and a very nice, satisfying, clunky switch. I'm going to show you what that switch does. It has modulation, both internal, external, 400 Hertz, 1000 Hertz, etc. And CW, which means like a pure sine wave output. It's got an N connector, which I fitted with an N to BNC adapter because I don't have any end-to-end cables. And it has a few extra functions and like a fine frequency adjustment, which works very interestingly. I'm going to show you inside of it as well. This is the modulation control and the frequency knob, which is very mechanically intricate and beautiful. And there's a trimmer for the amplitude, which also is still mechanical. Most of this thing is it's all vacuum tubes. There's one transistor inside, so I think that's an actually a retrofit. Voltage regulation for this thing is done with big twin triodes, 6080 triodes. It's got a gas discharge regulator tube, which serves that as a Zener diode basically for the regulated B plus supply. It's got about 20 vacuum tubes inside, if I counted properly, and I'm going to insert the link for the schematic and the service manual so you can see just how beautifully HP used to draw their schematics. It's just gorgeous. So, as you'd expect, this basically is a tuning capacitor, which it's a variable capacitor with interleaved plates, and moving this dial moves the plates further in not in contact, but overlapping. The lower the frequency, the more overlap, etc. The range switch actually does something different. The range switch actually changes inductors. So there's a very interesting mechanism inside that I'm going to show you that changes basically the inductance in the LC resonant circuit. This is the attenuator for the output, which goes from plus 4 dB to minus 125 dBm. Sorry, not dB, just dBm, or from 350 millivolts to around 100 nanovolts, which is, it's low, right? It's a very small signal. And I don't know what this knob does. It's probably for calibrating the crystal calibration. There's one 5 megahertz crystal and one 5 megahertz crystal, which you can tune somehow inside, and you measure the frequency you're trying to tune here. It's just a regular banana jack. I think this might be the same sort of dual amp that you would find on Fender twin reverb or reverb amplifiers from back in the day. It certainly has the same look, but usually I think the jewel on the Fender amps was not fully round. It was like a gemstone. It was faceted. Okay, so let me first show you the signal output on the spectrum analyzer. I'm just gonna leave this on the bench and not move it anymore because it's far too much of a hassle. It's giant. The actual rest of the case is over there somewhere because I need to show you inside. So I took it out of its case and to make it easier to film. So I'm gonna connect the output to the spectrum analyzer. I'm gonna move the camera so you can see the spectrum analyzer screen, and then we'll take a look inside. Okay, so wait just a second. Right, so as you can see, you're watching a very old computer monitor. Apologies for that. This is connected to the video output of the spectrum analyzer because it's far easier to film and because the screen on that thing is very dim. I'm going to have to replace the backlight in it. Sorry, I'm just gonna have to move this a bit like this. So the signal generator is now set for basically 125 megahertz on the dial. It's very close. There's a fine-tune knob that you can tune the frequency in just a bit, but I'm going to change the settings a bit on the spectrum analyzer so you can see how clean of a sine wave it actually produces. So if we go to span and we lower the span, which is 100 something kilohertz right now, you're just going to see at some point that the resolution bandwidth is 500 hertz and the frequency span is 21 kilohertz. So I don't know about you, but for a 65-year-old piece of test gear, that's very good. And you can see it's drifting a bit left to right, and it's not very stable, but it's just been turned on, and they say that for ultimate stability it needs to warm up for an hour first. So yeah, it works perfectly. There's just one, I think one detector diode dead in the whole thing, and I mean, Jesus, it's since before man landed on the moon. Like, wow, right? Okay, I'm gonna pause the video again, and then I'm going to take you on a tour through the instrument, through the insides of it. Be right back. Right, so first of all, apologies for the state of the thing. It is kind of dirty, but again, it's been in use for close to 70 years now, so bumblebee caps. This is, I think these are silver mica. This is like, it feels like very Mr. Carlson's lab right now. He usually deals with equipment from this era, or Usagi Electronics. So you can recognize the biggest brands in the industry like Dale resistors and Vishay. I think Vishay, I haven't seen a Vishay, but Dale definitely. And there's a definite Cornell de Blier silver mica capacitor around here somewhere. So, oh, and the electrolytics, the filter capacitors, they're all Sprague. So Sprague have made in the past capacitors that, although it's very not recommended to have them powered up like this after, like, it's a 65-year-old device. I keep saying that, but it blows my mind. Those capacitors degrade over time, but they still made them good enough that they haven't exploded, they haven't killed me, they haven't popped a breaker, they haven't tripped a fuse. Everything inside here works. Alright, so one interesting aspect, and I'm going to try and insert the part of the schematic that shows this, is there's this transformer here, and I didn't know what this transformer was used for. I thought it was a modulation transformer, but it didn't seem right because, yeah, there's not enough windings on it. This turns out to be a filament supply for one of the tubes inside the RF cavities in the back. I don't know why they needed it. I think it's probably the filament needs to be galvanically isolated from something else. And this was a very interesting way of getting an isolated filament supply. Although you can see the transformer here has a lot of filament taps. It's actually got, I think, close to 15 or something amps of 6.3 volts filament supply. I don't think it could have worked to have another winding to power that tube that needed to be galvanically isolated. It also runs at quite a bit higher frequency, I think, considering that you know, the transformer is rated for 5,000 hertz maximum. So I don't know why they chose to do that. It's very interesting. You can see all the strip board construction. All the resistors are placed very nicely in the middle, indicative of very high quality of assembly. Every solder joint is just perfect. The wires are soldered very well on all the terminals. You can see they're following the NASA standard of less than a full turn of wire over a terminal. It's just excellent. Like everything in here has lasted for 65 years. I'm sorry I keep saying that, but it's just it's astonishing to me. And these are I think these are the famous bumblebee caps that everybody was complaining about not being reliable. Well, look at them; they're very reliable. So even the capacitors withstood the test of time perfectly. If you look down in the bottom, I think I'm gonna try and show you here. This is actually the attenuator control, and I'll shift this thing and move it so you can see how the attenuator for the output actually works. It's very interesting. And then we're going to take a few bits off, just mechanical, mind you, and show you a bit of the inner workings in the shielding cavities. Okay, I'm gonna pause the video again, and I'm gonna show you the other side. Did I mention that this thing is heavy? Oh, it is very heavy. Part of that heavy aspect of it is that the power transformer is just giant. So we have the input winding, which goes from 50 to 1,000 cycles a second. This was made for so it could be used on like boats and airplanes and stuff like that, which all have higher frequency power supplies on board. This is a 207 volt winding, 125 milliamps. First 6.3 volt winding, second 6.3 volt winding, third. So we already have almost 15 amps, and basically just about 15 amps. And there is another 289 volts, almost 290 volts at 200 milliamp winding here. So there's a couple of voltage rails, high voltage rails in this thing. And these are the Sprague capacitors. Sprague, I don't know exactly the pronunciation, but Sprague capacitors, the main filter capacitors. There's a few more in the back here. These are all feed-throughs going into the cavity. This is all a big shield, and this is the jewel lamp and various controls on the front. Yeah, you can see there's a bit of rust creeping in on things. Maybe it's somewhere in a damp environment, but even despite all of that, it still works perfectly. Right, so this is the top of the instrument. I think I'm going to try and show you the back last because it's very, very hard to fit on my desk, despite it being a giant-ish desk. This thing is bench dominating. Right, so this is the main frequency indicator, the thing that goes around and shows you what frequency you're tuning to. And you can see there's two worm gears, basically. So this is the screw, and there's a worm gear in here. And these are synced because they're on the same shaft. So there's two actual tuning elements probably inside. This not only does it show the frequency, but also controls some variable capacitor inside. And you can see there is an indication that there's a tube inside, a 6BC4, and there's another tube in here, which I'm not entirely sure what it is. The attenuator for the instrument is this tube right here. If I try and reach over it and change the attenuation setting, you can see that thing moves, right? And something interesting else that moves is this cable. So this cable is the main output. It goes straight to the front of the instrument to the end connector. But how does it work? Well, the attenuator basically just moves the pickup point of the signal basically in and out further away from the source. So I'm assuming it's just basically attenuating based on the mechanical properties of the inside of that tube. So it's basically, I don't think this works up to down to DC because it couldn't, but this is a very nice way of having like a electromechanical interaction of the electromagnetic field in there. So it's further, it's like screaming at somebody from a further distance away. The further you are from the source, the weaker the signal becomes. I'm not entirely sure how it works, so I'm not gonna go into much more detail than that. But needless to say, it's very, very interesting. And as everything else in this thing, it's driven by a very, very finely made mechanical assembly. You can see it moving in and out. Okay, I'm gonna pause the video again. I'm gonna take this off and the cap so we can take a look inside at what's going on beneath that shield. I'll be right back. Right, so I don't know if you can see that Pesto, the lab cat, is still around. Maybe she'll want to show her face. What I wanted to show you is very interesting. So, first of all, this is the main RF generator assembly. There's 3 tubes marked on here, which are V6, and the schematics you can find them, V8, and this one in here is the V7. This is the buffer, this is the main RF oscillator, and this is the power amplifier. This one's is a 5675 tube, this one is a 5876 tube, and this is a 6BC4. These 2 tubes are the ones driven by that interesting, what do you call it, the transformer that I showed you on the other side. And if you look in the schematics, I'll try to insert a photo of the thing here. You'll see that the windings for the filaments are coming through here. Now, interestingly enough, this has been unplugged for a while. Don't put your hands into vacuum tube equipment. There's hundreds of volts with a lot of ampacity behind them in this kind of gear. Don't touch these unless you know what you're doing. You will die. Right, so you can see if you just carefully remove this. This is the filament socket, I think, for the vacuum tube. And you can see the feed throughs and stuff, and this all of the tubes that I found inside this device were actually custom made for HP. So this, for example, 6BC4 is a plain old triode, and it's made by RCA for Hewlett-Packard. And this is actually from 1967, I think, 22nd week of 1967. I'm sorry if you couldn't see that very well focused. Right, okay. And there's a few other components in here which are marked on the schematic as being very important. Yeah, probably they're chosen, tuned, specifically measured, and otherwise, you know, very finely selected components, only the best of the best, and the perfect value of perfect everything. That's how I imagine these things were built back in the day, because otherwise, how could they have lasted for 65 years? And interestingly, there was this tool inside, and I don't know where it goes. So this tool, where I think it's for removing something, but I don't know what. Oh, by the way, this is part of the power section of the power supply section of the entire instrument. These are 6080 tubes, which are in a ruggedized octal package socket, actually. And if I take one apart out of here, and if I manage to do that, how did I do this previously? Yeah, Excuse the dust. These are also made for Hewlett-Packard by RCA, and these are twin triodes. So you can see this is one triode element, this is the other. You can see the filament inside and the control grid, hopefully. Yeah, you can see it. And these are quite beefy, but because they're powered triodes and you know, triodes don't have a lot of gain, these are only have a transconductance of around 3 or 4, something like that. You could make actually a pretty nice push-pull amplifier with one of these, but you'd need very high drive voltage for them. Okay, I'm gonna try and put this back in here, like so, and they're nicely cinched in place with that strap. Again, every tube is made specifically for Hewlett-Packard, I think, to their requirements. I don't know. Or if you're Hewlett-Packard and you buy a million tubes like this, you know, this one's, for example, is made by Amperex. And these are the original tubes, I believe, for the entire device. This is a 12AU7, also common in guitar amplifiers. And this one over here, which is the one interesting one. This is a, no, not this one. There's a gas discharge regulator tube somewhere around here, but I don't remember which one it is. I'm gonna try and put this back before I break it more than it was. Like, I'll be right back with another side open. Did you think that I would leave you without showing you the beautiful glow of vacuum tubes? That's the discharge tube in there, responsible for regulating the voltage. And you can see the triodes have lit up, their filaments are lit up, everything is glowing nice and happily. The only thing we can't really see is the filaments for these two tubes in there, the 5675 and the 5876. So the oscillator and the power amplifier. Right, now I'm going to pause the video and I'm going to show you another side of the device. By the way, here's Pesto sleeping peacefully. That's what she does. All the time. She's grown so much. And she's a very cute little cat. Okay, let me cinch this improvised tripod mount I have here in place and show you what's inside here, because we can see there's some indication of what might lie inside: the amplifier tuner, the oscillator tuner, and the crystal calibrator. So yeah, Z1 and Z2 should be, I think, well, I'll be darned. I don't know what Z1 and Z2 are. C17B is the second section of a, you know, variable capacitor. C17A is the first section, etc., etc. And there's the quartz crystal Y and Y1 and another 2V109 inside here. So yeah, that's basically everything I can show you easily, because getting to anything else would require far more involved teardown of this thing, and I don't think I'll be able to put all the springs back together if I take it apart further than I'm already intending to. What's the story of this thing, first of all? I forgot to tell you. So it was going to be scrapped from the University Polytechnica of Bucharest, and a co-worker of mine who also is a teacher's assistant at the university or something like that asked me if I don't want to come and pick up some stuff, because they're gonna get rid of them. And I couldn't say no, could I? Like, this is a true piece of history, and I don't care about its financial value because I think it's pretty much worthless. Like, it's a good signal generator for I don't know what, but it's a decent one. Like, performance wise, it's still pretty good. It goes up to 400 megahertz, etc., etc. But the historical value is far, far more important than anything else for me in this thing. So, one last screw, and it was used as a, it was used in teaching basically. I think it was used in a, not, I don't think an RF laboratory or something like that, but in some sort of electronics laboratory at the university. Forgot one screw here. Right. So if we take a look inside, if I give you some more light, I apologize for that, you'll be able to see the main range switch for tuning. This is the last vacuum tube that was hiding in there. You can see it in here. There it is. It's another beautiful 6U8A. I think so. 6U8A. This is V9. Just a second. I'm trying to look for it on the schematic. V9. This is the, yeah, so considering that it's so close to the crystal, the schematic also says that it's the crystal oscillator. So this is basically, it's the active element in the crystal oscillator in this thing. Alright, so I'm gonna put this back in here very carefully, and I'm going to try and show you what happens. So if you change the ranges on this thing, if I can get to the range switch, where is it? Yeah, here. You can see that the entire mechanism moves and inserts a different inductor, basically. So in the first section here, we have these big wound inductors. For example, this one is just a plain short, but this one is two windings of, I think this is silver plated copper wire. Skin effect is very important at higher frequencies, so yeah. And in the other section here, we have some inductors as well. You can see wire wound. These are much, much higher inductance values. So these are obviously for the lower ranges. These are air core inductors, so much lower inductance values. And these are swapped in to, I don't think you can see the contact. I'm going to reposition, but there's a very interesting wafer contact that makes a connection with both of the things, both the inductors. And there's a detector diode in here. I don't think you can see it, maybe. Gold top, ceramic body, etc., etc. And there's another diode in there. These are, one of them is definitely for the power monitor assembly. So both of them are actually for that, but one of them is just for the meter tracking. It's on the schematic, and the other one is for basically for, I think, for regulating the output signal power, because you want it to have a constant output power for the entire frequency band. Right, so let me move the camera a bit and maybe we can try and see some of the other tubes in there. Just a second. So I did bring you in a bit closer, but I also couldn't help myself and I just had to show you this. I took it out from the compartment here. So this was the main RF oscillator valve. It's the 5675 triode. And you can see just how beautiful it is. Look at this. It's just gorgeous, right? That's the filament there. I don't know if you can see it, sorry. Filament, anode, and this is the control grid. and it's coaxial because it's an RF valve. This is the sealing port, that's where the vacuum was pulled out. It's just completely beautiful. Silver plated, minimizing skin effect as well. Just gorgeous. Made in 1967. I think the 22nd week of 1967. Right? This is one of the prettiest vacuum tubes I've ever seen. And I don't really know if I can take the other one out. And I don't want to risk it, so I'm just gonna leave it as it is. Actually, I'm gonna put it back in, and I'm gonna bring you back and have a look inside here. Right, one more aspect before I go and put that vacuum tube back in. If you can see that finger looking solution like there, that contact, that is connected to the plate of the variable capacitor, and it's ensuring a uniform connection to the anode of that vacuum tube. Just beautiful engineering. Oh, and this thing to the right here is a trimmer capacitor, and it's a vacuum capacitor as well. I'm going to show you underneath the rest of the thing. Okay, let's put this back in the holder before I make anyone sick, and let's get back to showing you the insides of this thing. Right, so as it turns out, these two parts here, so this one and this one here, are the anodes of the two vacuum tubes, the oscillator and the power amplifier. And what's going on is that the first one, the oscillator oscillates and generates the frequency output of the entire device, and the amplifier just gives it a bit more oomph in order to be able to drive the output. And the output of the whole device is this bit right here. You can see that diode over there, the detector diode I was talking about earlier, and this bit over here, that is for sensing the output level. More interesting than that is I don't think there's any physical connection between the output of the amplifier, the power amplifier, and the attenuator. This is the beginning of the attenuator here, and if I try and move it, let's see if you can see anything. So first of all, you can see this cable moving here. I think you can. It's pulling on it, and I don't think we'll be able to see inside there, but what's happening is that it's coupling power away from this thing, which is resonating, producing the signal output, and it's coupling power to the output, and the further away it is from the output, the less power it's coupling, so the higher the attenuation. This here is that interesting configuration of a leaf contact that I told you about. So you can see there's two contacts which are slightly spread apart, and when these wafers come in and contact them, with a very satisfying snap I might add, it just connects those two sections together, or to a various inductor or capacitor or whatever. Actually, to the inductors, because the capacitors, the plates of the capacitors are here, and I was correct about the tuning. Both of these two are variable capacitors, and both of them are driven by those worm gears that I showed you previously. Right, I think that's about it. I don't think I'm gonna try and take anything more out of this thing because it's far too pretty and far too interesting to destroy. I will try and fix it at some point. The meter, I told you, the meter that's supposed to show you the output level isn't working, and I suspect it's this diode because I measured it and it didn't really appear to be a diode anymore, although I might be wrong. So, I think that's about it for today. I do have a project lined up. It revolves around a app note written by the late great Jim Williams, and it's his 100 ampere dynamic load. I laid out a PCB. First of all, I simulated the schematic in LT-Spice, tried to update some of the components because since that thing was written, loads of parts have become obsolete or very hard to get, so I brought it up to the 21st century, hopefully. Sheesh. I made it so that it can make it with off-the-shelf parts. I designed the PCB for it. I got the components, and now I'm waiting for PCBs from JLC PCB to arrive. And we are going to finish that thing together. And if you want, I can go through the process of simulating the thing and the layout and talking about the thing in more detail. And I do have a few more things that I want to tear apart and discuss about, one of which was the DIY electrometer, which is basically this board right here, but I don't want to spoil it, so I'll leave it for next time. And the other thing is that big sampling scope that I talked about in that poll. It's completely dead, it's beyond repair. It's got new Vistors inside, which are incredibly dead, like not dead themselves, but they're incredibly obsolete technology, and I don't think it's worth repairing, so might as well completely destroy it piece by piece, examine every working aspect of it and see what we can learn from that. So, sorry it's been a long one again, a long video, but I'm happy to be back, and I'm waiting for your comments and suggestions on what to do next. So that's been all for today. Have a great weekend and take care of yourselves. Bye bye.